Hello everyone, welcome to the OneClass channel. My name is Marlon. I'm a second year student at the University of Waterloo, studying chemical physics with a minor in math. Today I'm going to be walking us through some high school level and college level chemistry problems. I'm going to be focused on Lewis structures today. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. So for our first one, we are trying to find out whether CH2Cl2 will be polar or non-polar. So for all of our questions today, we will first be counting the valence electrons. We need to count the valence electrons. Secondly, we will be checking out our formal charges. I'll explain why later. Third, we'll figure out its Vesper Theory, and then for the fourth part we'll be figuring out the net dipole moment. Okay, so for this one, as I said, let us begin with the valence electrons. So I have CH2Cl2. For my valence electrons, I have C, which is contributing 4 valence electrons per carbon, hydrogen, which is contributing 1 valence electron per hydrogen, and chlorine, that is contributing 7 valence electrons per chlorine. So for these ones, I multiplied it by 2 because I have 2 chlorines and I have 2 hydrogens. All of this is going to give me 4 plus 2 plus 14. And that's going to give me a total of 20 electrons to place. Okay, so let's go about doing that. So we need to pick our center, and we will typically be choosing the electropositive. Let me just write that out. Species. And the reasoning for this is because they tend to be able to make more bonds. While keeping formal charge low. This makes sense because they're electropositive because they like electrons. They lack electrons. They tend to be towards the left of the periodic table, and so they tend to be able to make the most bonds without messing up their formal charge. And so in this case, of course, we can't put in hydrogen, so we're going to put in carbon as our central, and then we can just place 4 bonds around it and just place the hydrogen and the chlorine. Okay, we can double check all of our electrons. 2, 4, 6, 8. So right now I have 12 electrons left over. I can fill in all of chlorine's octets, and that would now give me a count of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So all of my valence electrons are now taken care of. Okay, next up, as I said up here, we want to check out the formal charge. Now, the reason why we want to check out the formal charge is so that we can minimize it, because when they typically ask you for the Lewis structure, they're asking you for the lowest energy Lewis structure, and the universe doesn't like high charges separated and just large charge separation distances, and so we can deal with that by taking account of this formal charge, and if we minimize it, we're therefore minimizing the energy of the structure. So let's check our formal charges. Let me just write out the formula for you. So the formal charge will be the valence electrons minus the number of sigma bonds minus the number of lone electrons. So why I say sigma bonds is because when you really think about it, like for example, if I'm trying to do the formal charge of carbon, just as a quick example, for carbon, I have 4 valence electrons. Now, when I say sigma bonds, I'm talking about the electrons that it's contributing to each of these bonds. So here, carbon has made 4 bonds, so it's contributing 1 electron to each, so 1 by 4, which is 4, and then it has no lone electrons, and so its formal charge would be 0. For hydrogen, let's just do the same thing. For each of them, they all have 1 valence electron and are contributing 1 valence electron to the bond that they're making with the carbon, giving me another formal charge of 0. And lastly, on the chlorine, I have 7 valence electrons, minus they both have 1 bond, so 1 electron contributed to the sigma bond with carbon, and they both have 6 lone pairs of electrons, so giving me a formal charge of 0. So I can see that, well, first off, I would like to get the net formal charge to equal that of the molecule. So all of the charges add up to 0. The molecule has a net charge of 0, so I can tell that this is correct. And next up, I would like to minimize them. And I've done so, they're all 0. I can't minimize them any further. And so this is the best structure, is what that has confirmed. I've taken account of my valence electrons, I've taken account of my formal charge, so everything is good to go. So next up, I need to move on to the Vesper theory. So the Lewis structure just gave me the... Now, the Lewis structure method is great for electron bookkeeping. That's why we do it first, to figure out whether it's polar or non-polar. I need to figure out where my electrons are going, where they would best be placed to minimize charge separation, and to ensure that all of the valence electrons are taken care of. And so now, I move to the next step, and that's Vesper theory, which is figuring out its actual geometry. So, to do that, I first need to count the number of terminal groups on my central atom. I have 4, and none are lone pairs. So that notation is A for my central atom, X for the number of bonded groups, and I have 4 bonded groups. If for whatever reason, let's say I didn't have 4 bonded groups, instead I had 3 bonded groups in a lone pair, I'd write AX3 for the 3 bonded pairs, E1 for the 1 lone pair. So in this case, I have AX4 as we've just discussed. Okay, and so what that means is when I pull up my Vesper chart, this is called the steric number. Okay, so now that I have AX4, I can already tell you the electron geometry and the molecular geometry. So in this case, I'm lucky, they are both the exact same. The electron geometry is the way electrons are generally organized around the central atom. And so whether I have lone pairs or bonded pairs, it doesn't really matter. I have 4 pairs of electrons organized around my central atom. And so when I look for the electron geometry, I'm looking for the one that is telling me I have 4 groups of electrons arranged. And so I just come to 4, and it's the first one. I'm not accounting for which ones are lone pairs, which ones are bonding pairs. I'm talking about electrons generally. And so my electron geometry will be tetrahedral. Now, molecular geometry accounts for which ones are lone pairs and which ones are bonding pairs, because when you're talking about the molecule, you're talking about CH4. You're not thinking or talking about the lone pairs, you're talking about the atoms you have. So it's the way the atoms are arranged, not including those lone pairs. And so I would now move left according to however many lone pairs I have. This time, as I said, I have 0 lone pairs, so the electron geometry matches my molecular geometry, and so it will also be tetrahedral. Okay, now next up, I would like to draw it out. And so, yes, there are many ways that you can decide to place the hydrogens and carbons, which is something you must have wondered. I could decide to place, the hydrogen and chlorines. I could decide to switch them. I can decide to have the chlorines across from each other. Any of those would really be acceptable. Won't change the ultimate result. And so when I draw it, let's place Cl here. Have a Cl coming out, a hydrogen, and the hydrogen going up. Alternatively, let's say I didn't have that. Instead, I had this configuration. I'll show you in just one moment that it makes no difference. Okay, now let's begin thinking about our dipoles. So remember that our dipoles needs to point from the electropositive center to the electronegative one. Okay, and so between carbon and hydrogen, you can pull up a chart of electronegativities. You don't need to memorize any of the electronegativities. You just need to remember where things are relative to each other, which is super duper easy. Electronegativity increases going up on the periodic table and towards fluorine. Fluorine is the most electronegative one. And so if you just keep that in mind, hydrogen is yes up, but completely to the left. And so carbon is of course going to be more electronegative. Now between carbon and chlorine, chlorine is a little bit lower, but it is to the left more than carbon, and so it's going to be more electronegative. And with electronegativity, I don't only need to take care of the direction of the dipole, but the magnitude of the dipole, which means that when I'm talking about hydrogen compared to carbon versus carbon compared to chlorine, those two dipoles are going to have different magnitudes because they're representing differences in electronegativity. And so I'll draw it in a different color just to remind myself of that when I'm trying to cancel things out. And so even if I had it here, I'd have this coming out, this pointing in, and this pointing in. So already I can see that these dipoles won't cancel each other when I do add them up. These two will yield a dipole pointing downwards. And these two, we have one pointing downwards and one pointing slightly upwards. And so they will add in a different way, but it's not going to add to a dipole that can cancel this one out. So I can already tell that this one's dipole moment is non-zero. Write it out as net mu is not equal to 0. And same thing here, these ones will add up to yield a vector pointing upwards. These ones will slightly cancel, but not all the way because of this one's angular component. There's no way those two remaining vectors can cancel. And so again, my net dipole moment here will be non-zero. So as I said, no matter how you arrange the chlorines and the hydrogens around my carbon, the dipoles will not cancel. And so overall, I will get that CH2Cl2 is a polar molecule. Okay, and that's it for this question.